Hi, my name's Ed from UTS, and I'm excited to share our recent paper created in collaboration with Mission Systems and TAS. Together, we developed a system to enable a team of robots to reason over imprecise human intents in order to provide useful observations of an environment that a human must move through. Multi-robot systems are naturally suited to large-scale exploration tasks. In particular, heterogeneous robot teams can be deployed to take advantage of their multifarious abilities. If robots could reason over human intents, they will be able to collaborate more effectively with humans, instead of requiring constant attention. We developed a system to this end, and deployed it in large-scale field experiments. We consider a multi-robot exploration task where the robots are influenced by uncertain human intents. A human, shown fuchsia here, must move through a hazardous environment following a high-level objective. In our case, this is to reach a given green goal location while avoiding hazards, shown red. A team of robots comprising aerial and ground platforms, in blue and orange respectively, is to provide safety to the human by exploring the environment in advance to find these hazards. Robots should be able to infer the intended human path, drawn dashed, from their high-level objective, and prioritize areas near that path to provide useful information to the human. The inferred path should dynamically update to reflect new information, in this case, newly identified hazards. Our proposed system is shown here. High-level control of our system is performed by a behavior tree. This defines fail-safe behaviors for each robot to ensure safe operation. It also handles robust startup behavior and facilitates switching between teleoperation and autonomous behaviors in the field. A behavior tree architecture was chosen for its transparent and robust operation and its extensibility to more complex behaviors in future. Our autonomy pipeline requires several kinds of map, each used in a different way. Predicted observations are made using a 3D voxelized map of the environment. A 2D occupancy grid is used to account for the obstacles on the ground while planning agent trajectories. This is converted into a discrete graph of viewpoints that each robot could observe the environment from, which is used in our high-level planner. Robots should know what could be observed from each viewpoint. This is calculated by voxel ray. Voxel ray performs GPU-accelerated ray tracing on the voxelized map of the environment to rapidly predict what can be seen from each viewpoint. A custom Human Intent Inference module converts their high-level objective to a predicted path through the environment. In our case, the high-level objective is to move to a goal location while avoiding obstacles and hazards. When new hazards are detected, the system adapts the predicted path. We present two methods, a simple graph search-based planner and a more complex method utilizing random signal temporal logic. The latter method could be extended to more complex objectives in future. Decentralized Monte Carlo tree search is an extension to single-agent MCTS to enable efficient and intelligent multi-robot decision-making. Agents individually simulate the outcome of making different choices, in this case choosing different locations on the discrete viewpoint graph to visit. Future plans are represented as a probability distribution, which is occasionally transmitted to other robots in the system to inform their future planning. We developed a custom reward function based on voxel ray, such that the robots prioritize observing regions near the inferred human path and explore different areas to one another. There are also two secondary components that are not explained in detail but are required for autonomous operation. We developed an autonomous hazard detector that identifies hazards within images captured from the robots. This is based on the well-known DETR architecture, trained for our specific scenario. Each robot also requires low-level systems to enable autonomous waypoint following. These include localization algorithms, LiDAR-based obstacle detection, and a local planner to generate the motor commands to move the robot to the goal. Our system was demonstrated in simulation and large-scale field experiments. Simulations were performed with 4 robots to demonstrate the scalability of our system. This video shows one trial. Maps of our field environments were used in these experiments. We used our graph search-based human intent inference approach to focus the results on the ability of robots to choose useful trajectories. These results show the robots spread out and observe different portions of the environment, prioritizing unexplored areas near the inferred human path. When hazards are detected, the inferred path changes. The robots react to this by choosing future plans that align with the new intent. Our hardware experiments were performed in an environment measuring roughly 600 by 400 meters, containing open areas, long grass, and dense trees. Here we show an experiment with a ground and aerial robot. Our temporal logic-based human intent inference is used, which predicts suitable paths and reacts appropriately to newly detected hazards. As in simulation, the robots explore distinct areas of the environment along this path. Robots observe a large percentage of the area around the human in advance, demonstrating their ability to make useful observations of the environment. We faced numerous real-world issues, such as the communication dropouts observed in this trial. However, the algorithms proved resilient to these difficulties, with each robot continuing independently until communications were re-established. Our paper also explores many of the important lessons we learned over the course of this multi-year project. Lessons specific to our application include the trade-offs in predicting observations in real time, and difficulties in accurately inferring human intents. We also discussed lessons applicable to more general multi-agent field robotics applications. These include the need to design algorithms that are generalizable to different robots or areas of operation, as well as ways to exploit the advantages of heterogeneous multi-robot systems. Finally, our paper highlights several open challenges for the community. These include ways to test and optimize high-level algorithms, predicting more complex human intents, moving beyond the offline maps used in our system, and reliable off-road locomotion for ground robots. In our paper, we have shown the ability of our system to aid humans in field environments by providing useful observations determined by inferring uncertain human intents. In future, we plan to incorporate online mapping algorithms, improve a range of temporal logic formulae that our system can infer intents from, and deploy with larger real-world teams. For further information, please see our accompanying paper. Once again, we'd like to thank everyone at UTS, Mission Systems, and TAS that has been involved in making this project a success.